P of A given B equals P of B given A times P of A divided by P of B. 5 symbols, that's it. Every spam filter, every speech recognizer, every classical machine translator, half of naive Bayes classification, all of Hidden Markov Model decoding. Same 5 symbols, somewhere in the guts. This is Bayes' rule, named for Thomas Bayes, an 18th century minister who worked it out for gambling problems. Today it's the most ubiquitous formula in machine learning. And by the end of this video, you'll never forget what each symbol does, because there's a meme. Last video we talked about the curse of dimensionality, geometry gone wrong. Now we swing all the way over to probability. Because when your model outputs a distribution over hypotheses, HEREs, how likely each next word is, the whole game is about dating that distribution as evidence comes in. Bayes' rule is the update. Here's the puzzle. Your system starts with a belief, a prior distribution over possibilities. Then you observe some data. Question: how do you turn what I believed before plus what I just saw into what I believe now? There is exactly one mathematically correct answer. Bayes gave it. Today's 3 beats. First, the derivation. 2 lines of conditional probability. That's where Bayes' rule comes from. No hand-waving. Second, the meme. Prior times likelihood divided by evidence equals posterior. Once you internalize this, you never forget. Third, the sightings. Spam filter, speech recognition, statistical machine translation. Same rule in different clothing. Beat 1. Where Bayes' rule comes from. Start with the definition of conditional probability. P of A given B equals P of A, and B divided by P of B. That's just the probability that both A and B happen, normalized by the fact that we know B happened. Simple. Same thing, symmetric. P of B given A equals P of A, and B divided by P of A. Now the trick. Both definitions have that joint P of A and B on the right, so set them equal to each other. P of A given B times P of B equals P of B given A times P of A. Divide both sides by P of B. You get Bayes' rule. That's it. That's the whole derivation. 2 lines. Which is deceptive. Because the formula is trivial. But the pattern, inverting a conditional probability, is one of the deepest ideas in reasoning. You go from P of data given hypothesis, which is often easy to write down, to P of hypothesis given data, which is often what you actually want. That's Bayes doing all the work. Beat 2. The meme. Look at the formula again with new labels. P of hypothesis given data equals top of the fraction, P of data given hypothesis times P of hypothesis. Bottom of the fraction, P of data. Rewrite in English. Posterior equals likelihood times prior divided by evidence. Say it out loud a few times. Prior. What you believed before seeing the data. Some hypotheses are just more plausible a priori. Likelihood. How well the hypothesis explains the data you saw. Evidence, a normalizer, just makes the whole thing a proper probability distribution. Posterior, what you believe after. Prior updated by evidence. That's the whole intuition. Here's why priors matter. Even in NLP, where people mostly compute frequencies rather than Bayesian posteriors, a rare word that fits the context perfectly might still be less likely than a common word that fits it okay. Prior probability of the word affects the answer. Ignore priors and you generate hallucinated technical vocabulary that never appears in real text. Beat 3. Sightings. Sighting 1. The spam filter. You get an email. You want P of spam given words. Rewrite with Bayes. P of words given spam times P of spam divided by P of words. Now everything on the right is countable. You have a big pile of spam emails to count word frequencies in. And you have a much bigger pile of ham emails to count against. That's naive Bayes classification, deployed in every email service since 2000. Sighting 2. Speech recognition. You have audio. You want P of words given audio. Rewrite with Bayes. P of audio given words times P of words divided by P of audio. Now you have two models: an acoustic model computing P of audio given words, a language model computing P of words, combined via Bayes. Whether your acoustic model is a hidden Markov model or a deep neural network, the Bayes skeleton is the same. Citing 3. Machine translation. Brown et al., 1993. Same trick, foreign language on top. One caveat: modern NLP is mostly frequentist in practice. Big neural networks compute P of next word directly. They don't explicitly write down a prior and a likelihood. But the reasoning pattern is still Bayes. Prior beliefs get updated by evidence, and the update is mathematically valid because Bayes says so. The formula lives inside the intuition, even when it's not on the whiteboard. 3 takeaways before the quiz. 1. Bayes' rule is 2 lines of algebra from conditional probability, trivial to derive, deep in what it lets you do. 2. The meme, prior times likelihood divided by evidence equals posterior. Say it out loud until you don't forget. 3. Every classical NLP system, spam filter, speech recognizer, machine translator, is Bayes' rule wearing a different costume. Quiz 1. What does Bayes' rule let you compute? A. The mean of a distribution. B. P of hypothesis given data, when you can easily compute P of data given hypothesis. C. A p-value. Or D. A determinant. B. The inversion. Getting P of hypothesis given data is what you want. Getting P of data given hypothesis is usually easier. Bayes flips one into the other. That inversion is the whole reason the rule matters in machine learning. Quiz 2. What's the meme for Bayes' rule? A. Odds against odds equals log likelihood. B. Prior times likelihood divided by evidence equals posterior. C. F equals MA. Or D. Regression to the mean. B. Prior times likelihood over evidence equals posterior. Each word maps to one term of the formula. Once you've drilled the meme, you've drilled the formula, and you can rebuild the whole thing from memory forever. Quiz 3. Which of these NLP systems is not Bayes' rule in disguise? A. Naive Bayes spam filters. B. Classical HMM speech recognition. C. 1990s statistical machine translation from Brown et al. Or D. All 3 ARE Bayes in disguise. D. All 3. Spam filters use naive Bayes explicitly. Speech recognition uses Bayes to combine an acoustic model with a language model. Statistical machine translation uses Bayes to combine a translation model with a language model. Same rule, different costumes. Back to the puzzle. 5 symbols. Every classical NLP system, and even inside modern LLMs, Bayes-shaped reasoning is quietly running. That's the whole toolkit. Probability, information, geometry, Bayes. Next video wraps Lecture 4 and previews Lecture 5, where we finally get to word embeddings, the punchline of everything we just built. Next time, Lecture 4 wraps 9 videos of the math toolkit in one recap, plus a preview of Lecture 5, where we take everything we just built and use it to teach computers what words mean. Sort of. Hit subscribe.